Welcome to this lecture on level shifters in module 4. So, we will first discuss a simple level shifter, cross coupled level shifter, and then an improvement upon it which is current mirror based level shifter, and then Wilson current mirror level shifter which handles the static current issues in current mirror based level shifter. So, why are these level shifters important in near threshold voltage regime? This is because different modules, different parts of an IC could be working in different VDD domains. So, you would need to change the levels, logic voltage levels when moving from one VDD domain to the other, especially the logic level 1. Its value would change when moving from one VDD domain to another VDD domain. Likewise, in a multi-chip packaging, for example, in 3D ICs or SIP, you would find that different ICs could be working in with different supply voltages. Even in that case, you would require level shifters to change from one voltage domain to the other. Now, we are interested in ultra low voltage operation of circuits. So, we are interested in say a near threshold voltage to a nominal voltage level shifting. So, when you want to shift the levels from a high voltage to a low voltage, you could be using a simple inverter when shifting from high voltage to the low voltage. So, VDDH is the higher voltage and VDDL is lower voltage. When this turns from 0 to 1, the P MOSFET is off, N MOSFET is on, and you would get a 0 here. You would turn this from 1 to 0. And when the input turns from level 1 to logic level 0, the P MOSFET is now on and N MOSFET is off, and therefore, you would turn the output to VDDL, which is logic level 1 in the lower voltage domain. Stop. Yeah. So, in this case, begin. In this case, there is no static leakage, and a simple circuits, we can have simple inverter to convert from the higher voltage to lower voltage. However, for shifting voltage levels from low to higher voltage, we require special circuits. So, this is a cross coupled level shifter where this is the input lower voltage level. So, this is low VDD level, and so this is VDDL, okay, and you would see that this supply voltage is higher voltage. So, A and B would switch from 0 to VDDH and from VDDH to 0. So, that is how you will, so the output voltage that you see would be 0 to VDDH, and the input voltage is 0 to VDDL, lower voltage. Okay. Now, this lower voltage is near threshold. So, the transistors are almost at the edge of the cutoff region. So, the currents through them, even when their input is high, would be much smaller than the currents through these transistors which are operating with a supply voltage VDDH, which could be a nominal voltage, okay, nominal VDD of the PTK. So, how does this work? Suppose the input changes from 1 to 0, then M1 is put off and M2 with a little delay, M2 is turned on. Once M2 is turned on, the voltage at node A is pulled down, but initially M1 was turned on, and therefore, B was at a very low voltage near 0, it should have been at 0, okay, and therefore, M4 is already on. So, M2 is pulling this down because its gate voltage is now VDDL, but M4 is on because of the previous state. So, previous state was that A was VDDH. So, here A is turning from VDDH to 0. So, that would require that M2 should be the current through M2 should be larger than the current through M4 for it A being current through M4. So, that would require M4 to be off, M4 to be off, but B is initially at a low voltage near 0. So, therefore, M4 is initially on. So, as A is pulled down, M4 will have a non-zero VDS and it would have a current. That current should be smaller than the current that is going through M2. So, we may note that initially M4 is on since B is initially at VB equal to 0. It goes, so now once that happens, A is now, so the value at A would be pulled down to 0, and once it is pulled down to 0, M3 is on, and since M3 is on, because of then M3 will charge B to a high value, because M1 is anyway off, and therefore M4 will be completely put off, but that would require this condition to be followed initially, okay, till the time M4 is not off. So, it should be ensured that M4 is turned off, okay. So, that is a design requirement. Now, let us see switching from 0 to VDD. So, 0 to input switches from 0 to VDD-L. Now, this switches from 0 to VDD-L. So, this now turns on. So, now this is pulled down and this is switching, the input of M2, gate of M2 is switching from VDD-L to 0. So, this is off. So, again the same phenomenon should be happening in the opposite direction, and you should be able to supply a current through M1 which can counter the initial current through M3, since M3 is initially on. It will turn off eventually if the design is proper. Now, let us look at an improvement over this break. Static current, एक मिनट नहीं है ना static current, क्योंकि M4 ऑफ हो जाता है eventually. Static current next वाले में आता है. So, now let us discuss the current mirror based level shifter. So, in this, when input goes from 0 to VDD-L, M1 turns on. Once M1 turns on, now VA is pulled down. Since VA is pulled down, VGS the magnitude of VGS of this transistor M3 keeps on increasing. The magnitude of VGS of transistor M3 keeps on increasing because the node A is being pulled down. That increases the magnitude of VGS of M4 also, okay, and therefore M4 also now starts supplying larger current. Now, but M2 is off, but M2 is turned off here, okay, because input is going from 0 to VDD-L. So, therefore, M2 is turned off and node B is charged. Node A would be charged according to the current ratios of M3 and M1. Node A would come to a static voltage based on the current ratios of M1, M3 and M1. So, IM3 is equal to IM1. This determines the final value of VA, node A, okay. So, but whatever be that value, M4 will keep charging till the VDS of M4 is 0. IM4 would be non-zero till VB is equal to VDD-H, okay. So, you do not have the problem that the transistor M1 and M2 should be very large sized, which you had in cross coupled inverters. So, need not be large sized. It will whatever be the value of final VA, the value of VB would be VDD-H, because M4 would keep on charging till its VDS is 0, because its VGS has a non-zero, has a magnitude which is larger than say threshold voltage. So, its VGS is sufficiently large and it does not change, because VA has come to a constant value where IM3 is equal to IM1. But the problem is that there is a static current flowing in this wing. So, that is a huge power supply cost, because that static power current is coming from VDD-H. So, it will be VDD-H. So, the static current would be the static power would be VDDH into IM3, this final value of IM3. Okay, that will keep on flowing throughout. So, that is an issue. Now, suppose we change the input from 1 to VDD 1 to 0. So, here 1 is VDDL. So, this goes to 0. So, therefore, the current IM1 goes to near 0 and therefore, IM3 must also become 0. So, VSG becomes equal to VTHP, the threshold voltage of the P MOSFET M3. So, that will put M3 off, that will also put M4 off, and gate of M2 is now switching from 0 to 1, M4 is off and therefore, B will be pulled to 0. So, the problem here is static current. Let us now discuss an improvement upon this, where the static current is reduced to near 0. How is that done? So, now a transistor M5 P MOSFET is kept in between M3 and M1. What is the advantage of this? So, where did we have static current? When input was VDDL, input was 1. Now, suppose input is VDDL, input turns from 0 to 1, VA is initially 0, VA is initially 0, M5 is on initially, okay, and now this is pulled down. So, it will first discharge C and there is a current through this, and that current must be supplied by M5. So, VB will also go to a lower voltage, so that the magnitude of VGS of M3 is increased and magnitude of VGS of M5 would also increase, and therefore, as M5 is initially on, so magnitude of VGS of M3 would increase. M1 was off, M5 was on because A was 0 initially. Initially A was 0 and therefore, M5 was on, and input is switching from 0 to 1, M5 is already on, and therefore, the current of through M1 should also flow through M3, and that would reduce the value of VB, because and that would increase the magnitude of VGS of M3, and therefore, the magnitude of VGS of M4 also. So, now M4 would supply current, and that current would charge node A, because M2 is off, input is turning from 0 to VDDL, the gate of M2 would go to 0, okay. So, now and A would go from, so it would keep on charging, but once, so VB would have a certain value, but once VA reaches higher values, M4, the current through M4 would keep on reducing, okay, and current through M4, since it reduces, current through M3 also reduces. So, the magnitude of VGS of M3 should keep on reducing, that is VB should rise, VB should rise in value, and once VA is so high that VB rises to VDD minus VTHP, VA would, so the transistor M4 would turn off and VA would now almost not increase further, okay. So, that is, so therefore, this switches from 0 to a VA, where VA is this constant value which is being seen here. So, the input switches from 0 to VDDL, okay. VA switches to a certain voltage, it does not go to VDDH, because before it goes to VDDH, M5 is turned off, because as VA rises, the current through M5 reduces, and VGS, magnitude of VGS of M3 and therefore M4 also reduces, the current keeps on reducing, and M5 is then turned off, and once M5 turns off, M3 also turns off, its VGS reaches VDD minus magnitude VTHP, okay. So, and that value of VA is this is not VDDH, okay. So, here the problem of static current is handled, static current in this wing is now 0, but the problem shifts. So, when you are, so this is now at not at VDDH, but a lower voltage than VDDH. So, the P MOSFET is not completely off. So, what one must ensure is that this VDDA, this VA should be smaller than VDDH minus magnitude VTHP. Ensures that this condition would ensure that the P MOSFET of inverter INV1 is off, is in off state, sorry, greater than. So, if VA is greater than VDDH minus magnitude of VTHP, the P MOSFET of inverter 1 INV1 is in off state. So, the static leakage, there is then little or negligible static leakage through, there is no static leakage practically through INV1. Otherwise, if VA is smaller than VDDH minus VTHP, when the input of in INV1 is 1, is logic 1, you would see that there is a static leakage, static current because the P MOSFET is on for INV1. So, we would be reducing or making the static current in this wing 0, but we would then have a static current in the inverter. How does the turning off of the, when input turns off, what happens, how the transients behave in this current mirror based level shifter. Suppose input A is turning off VDD from VDDL to 0, what would happen? Input is turning from VDDL to 0, so this is turning on from 0 to VDDL. Okay. Now, A was at the value VA which we were discussing. Now, this would start discharging. M4 is off because VB was VDD minus VTHP initially. So, V in is going from 0 from VDDL to 0. Okay. So, initially VA was, so initially node A was at a voltage VA. Okay. Node C was at 0 and node B was, M3 should be off, and therefore, no M5 is also off because node A is at a higher voltage and node B is at VDDH minus magnitude VTHP initially. Now, you are turning off M1, okay, and turning on M2. So, A would start discharging. So, once A starts discharging, M5 would turn on. So, since M2 is turned on by a VDDL, so what happens? Now, VA is pulled down, okay. As you can see here, VA starts getting pulled down, but that will put on M5. So, that turns on M5. So, if M5 is turned on, there is a current through M5 and that is the current which also flows through M3. This turns on M5 and M3, okay, which in turn turns on M4, which is not what you wanted, okay, because M2 is turned on, you want VA to reach 0. So, therefore, there is now a current through transistor A and this current counters the current through M2. So, this is the region where M5, M3 and M4 are all turned on, okay. But VA further reduces and VC keeps on increasing, but this also keeps VC increases due to IM3, okay, and that, so VB also keeps on increasing. So, this again turns off M3 and then M5, okay. So, once they are turned off, M4 also turns off and then eventually node A goes to 0, okay. So, this is how the input switching from VDDL to 0, the transient phenomenon would look like this, okay. What about the input switching from 0 to VDDL? So, previously we were looking for the input switching from VDDL to 0. Now, we are looking for the transient phenomenon, how it happens when input switches from VDDL to 0, 0 to VDDL. So, 0 to VDDL. What was the initial value of C? What was the initial value of C? It was a high value. What was the initial value of B? this was VDDH minus magnitude VTHP because M3 was off. Vc was also at a higher value because A is 0, M5 was on and its VDS of M5 can be 0. So, it is also nearly at VTD minus VTHP, but you have switched on V in. So, Vc starts discharging, okay, and once Vc starts discharging, you would find that there is a VDS developed across M5 and there is a current through M5 and therefore, there would be a current through M3 also eventually and that would reduce Vb starts falling, okay. And once Vb starts falling, M4 is turned on and M4 is turned on, Va starts to rise as is being seen here, Va starts to rise. And once Va rises to a value sufficient to turn off M5 and to reduce the current through M5, you find that the rise of Va is very small and eventually M5 is turned off and therefore M3 is also turned on off and Va reaches a steady state value as we had seen earlier. So, in this lecture we discussed the importance of multi-domain level shifting in multi-power supply domain scenarios in a single IC or in different ICs in a single package, and we discussed important level shifter circuits, their operation, their limitations and their transient behavior. Thank you.